what we're going to do today, to start with at least, is that we're going to finish off the intro to series, and we're going to look at these questions here, which are, well, 3 of them are telescoping series, and 1 of them is partly a telescoping series and partly something else. And then we start, my goal is to get this finished as well, 11.3. And 11.3 is 2 more tests. We're going to look at a test called the integral test and another test called the P-series test. And what they allow us to do is to essentially tell if a series is going to converge or diverge. And I'm sure I mentioned on Monday that there are something like 11 to 13 tests, because in different situations you need to do different tests to find out if a series converges or not. So let's jump right into the first one, number 14. In this one, we're going to be using a telescoping series, and that involves typically, in many cases at least, using things called partial fractions. So, right, that's the guy we're going to be doing. So let's do the algebra piece first. This guy has to be written in a format where the denominator is factored. Then I can use partial fractions. In fact, I'm going to put this term first because I want the smaller one first typically. And then I want to put the second one there, right? Now, when you take a fraction and you break it into its 2 pieces, these are called partial fractions. And our quest is to find out what number A is and what number B is, because once we've done that, we can then move on to the next phase of telescoping series, which allows us to essentially look for a pattern and see what's left over. Because very often when you have telescoping series, you have 1 or 2 guys at the beginning that stay alive, everybody in the middle gets killed off by somebody, and 1 or 2 guys at the end that are left alive. And you can typically tell whether a series is going to converge or not because of that.
Am I missing something? You got n+2, right?
Oh, you're right. It's a long day. n+1. Right. We use the technique called the cover-up method. So here goes. I want to get the n-1 term, right? That's A. So if I can use something rather than my fingers. You cover up the n-1 term here. Right. You then plug into what's left, that's up here, what's left up here, the value of n that makes this 0, which is 1. If you plug in 6 over 1 plus 2, 1 plus 1, you get 2. 6 over 2, you get 3. We call that the cover-up method. It's kind of magic, but it works really well. Now, let's suppose I want the second one, the number that belongs to the n+1. Cover up the n+1 and find the value of n that makes this 0, and that happens to be -1, and plug it into what's left, and you get this guy. Now, if you do telescoping series correctly, this fraction will break into 2 pieces, and each piece will be the same number on the top, 1 plus 1 minus. So if you see that, you know you're on the right track, right? That's just what's going to happen. So this guy up here is now going to be written as n equals 1 to infinity. The first guy, take away the second guy. So that is exactly the same thing as that. It's just written in a different format. And I'm going to write it down here again. Then the next thing we do Can I change that number to 2? Right. The next thing we're going to do is write down the first 3 or 4 terms, right? So plug in n equals 2, n equals 3, n equals 4. And if you're wondering why I changed that from n equals 1, if I plugged n equals 1 here, I'd get 3 over 0, which would be infinity, and that's not really a good idea. So if you plug in 2, you get 3 over 1, take away 3 over 3. Right, that's what you get if you plug n equals 2 in. The next number you should plug in is n equals 3. So let's see what we get. 3 over 2, take away 3 over 4. And then you plug in the next one, which would be what n equals 4. And let's see what you get. 3 over 3, take away 3 over 5. Let's put one more in. N equals 5. And what you're going to get here is 3/4, take away 3/6. Now this could keep going for eternity. But what we do is we imagine that we stop at some arbitrary value n. So essentially the last term would be that one, right? And then if things work out the way they should, you should do, which is a little bit harder to figure out, what the term just before that one would be like. So what I'm looking for is, if you took 1 away from this guy, you'd get a 3 over n. So that would be the one just before him. If you took 1 away from him, you'd get 3 over n minus 2. So you do 2, 3, 4, probably 4 at least terms at the start, and then a couple of terms at the end.
Yeah, I can't
That
see
one's,
the bottom line.
there we go. The terms at the end, right? Now that one is him. And this one is what you would get if you took him and replaced the n by n minus 1, right? So that's essentially what the term just before this one would look like. And then some cool things are going to happen. That guy gets killed off by him. That guy gets killed off by him. That guy would get killed off by somebody here, and that guy would get killed off by somebody here. And in fact, there are only 2 guys at the beginning that don't get killed. 3 over 1 and 3 over 2. All the other terms, the ones that are here and the ones that could after it, something later on would be the same value but negative, right? So you've got a plus guy, take away a negative, or a negative guy and a plus. They all die. Now, if the 2 guys that survived are at the front, then the math tells me that the 2 guys at the end, so I call that the front and the end, right? 2 guys at the front alive, 2 guys at the end alive. So what does that look like? It looks like I have this guy and I have this guy. So that entire series basically ends up being just, in this case, 4 terms. And then you do the clever part. What would happen if we didn't stop at n, but n went infinite? Well, that would still be 3. That would still be 3 halves. Wouldn't that be 3 over infinity, which is 0? And wouldn't that be 3 over infinity, which is 0? So basically, you are left with 1.5. So we have now found out that the original series, this one, converges, and not only do I know it converges, I know it converges to 3 halves. And the trick, this is called the telescoping series. The trick that we used of everybody dying except a couple of guys at the beginning and a couple of guys at the end.
So a quick question. Why did you have minus 3 over 2? I thought it was a plus in between there.
Oh, I didn't do it right.
Oh, okay.
So the right answer is 9/2. So it converges to 9/2. Are we good? Okay, let's do 16, which is very similar to this one. And then we'll show you the other two, which are not really, well, one of them anyway is not that similar. So this one is, I think it's 18. Let's check the number. No, it's not. 16. So it's 18 over n plus 3 from 1 to infinity. So I'm going to take this guy and turn it into his partial fractions. So that's essentially step one. Okay, I want this number A, the guy that belongs with the n. Go to the original and cover up the n. That's kind of why it's called the cover up method. The value of n that I'm going to use is 0, because that's what makes this 0. 18 over 3 gives me 6. Yes? Question? Okay. Second one then. N plus 3. Cover up the n plus 3. No, I have to do my finger this time. Cover up the n plus 3 over here. Put in -3 for what's left. 18 over -3 gets you -6. In fact, we kind of know what's going to happen. If that's 5, won't that be -5? If this is 2, won't that be -2? Right? If we do the first one right, you know what the second one's going to be. So we have changed the original series into its partial fractions. Okay, so that's step 1 finished. Right, step 2 coming up. In step 2, you plug in, find the first 3 or 4 or 5 terms, whatever you think you need to see the pattern that is eventually going to develop, where at some point or another, you're able to tell which ones are left alive, because everything else is going to die. So this one, I think, needs quite a few. If you plug in 1, you get 6 over 1, take away 6 over 4. And that's what you get when you put n equals 1 in. If you plug n equals 2 in, you get 6 over 2, take away 6/5. If you plug in 3, you get 6 over 3, take away 6 over 6. If you plug in 4, you got 6 over 4, take away 6/7. And I think I want another one just to see if the pattern's obvious. And plug in 5, you get 6/5, take away 6/8. And that could continue for eternity. Well, let's see if there's any patterns going on here. Do you see this guy here? Gets he killed off by that one. Do you see that 6/5? Gets killed off by that one. You're going to have to trust me on this one because I didn't do enough terms. This guy here will eventually get killed off by the one that would be over there, eventually. So what does that look like? It looks like that one, and that one all are going to survive. So it's 6 over 1, 6 over 2, 6 over 3, plus some guys at the end. Now I'm only going to put the last guy in. Technically, shouldn't I put the second last guy in and the first last guy in? But all I'm going to be looking at is what does it converge to? Would you agree that these guys here, no matter how many I wrote down, aren't they all just going to be whole loads of different zeros? So that means that the thing converges. And it converges to 6 plus 3 plus 2. It converges to 11. So if you did this series, it converges to 11. Okay, any questions? It's a very specific trick for a very particular series that look like these guys. And this trick involves splitting into partial fractions, writing down as many terms as you want, and seeing at what point do you get some guys left alive and everything else dies. And if everything else dies, then these are the ones that are left alive. That's what it would add up to, and it will converge. Are we good?
So the expression 18n times n plus 3, that converges at 11.
It converges. In this case, to 11. I might have overshot that one. There we go. Okay, let's show you some special cases. This one is considered a telescoping series, but it doesn't look like any of these guys, but it's still considered one. So let's see how it works. In this question, what you have to realize is that you can rewrite this guy as, well, do you know, I'm going to pull out the 7 because it's common and just focus on this. So it's the log of n, take away the log of n plus 1. Are you happy about the log of a division can be rewritten as the log of the top guy, take away the log of the bottom guy? Now, because it's written in this format, I can then basically just plug in n equals 1, n equals 2, n equals 3 until I see a pattern. If you plug n equals, can we pretend the 7's not there for a minute, and then whatever answer I get, I'll stick a 7 in front of it later. So if you plug in 1, you get the natural log of 1, take away the natural log of 2. And then you add the next one, you get natural log of 2, add the take away the natural log of 3. So that's what happens when you plug n equals 1 in. That's what happens when you plug n equals 2 in. If you go to this one, you're going to get natural log of 3, take away natural log of 4. I think I can see the pattern already. Won't this guy get killed off by that one? Won't this guy get killed off by that one? Can you see only one guy's going to get left alive on the front? And that guy, well, and let's put the last fella in. The last one would be these two guys, right? That's the end. Right. If the first one, log of 1, makes it alive, which one of these two will also make it out alive? So if the front one works, which one of these two will survive?
The second one.
Okay, which is correct. Which means that this thing ends up being the natural log of 1, take away the natural log of n plus 1, right? That's essentially the only two terms that would exist if you stopped at some, arbitrary place n. Now, what happens when n becomes infinite now? Well, that's 0 and that's infinity. So that means that this series diverges.
Hey, Professor.
Yes.
Real quick, why did you cross out that natural log of n and turn it into natural log of 1?
The natural log. The natural log of 1 came from over here.
Okay.
So it wasn't that guy. The reason this guy gets crossed off is there'd be a guy over here that would kill it.
Okay.
And the trick is that if a guy at the front lives, then there's going to be a balancing act. One of the guys at the end is going to survive as well. So if a guy at the front works, a guy at the end works, right? They're the two that'll make it. And that's the answer to that question. It's basically converging. Now, the final question is 18. I'll put it here. This guy contains a part of it, which is this fella here, and this is a telescoping series. And you could do a calculation on it, and you'd get the answer. I believe the answer is it adds up to 5. This guy here, however, is much more important. Right? So the way you're going to do 18 is you're going to split it into 2 pieces. That's going to be the first piece. And then that guy is going to be the second piece. And I'm going to focus on this one. You might not recognize this, but this is going to be a geometric series. And I'm going to rewrite it to make it a little bit more obvious. It can be written like that. Then it can be written like that. Are we good so far? Now, what is R equal to here? What is the common ratio for this geometric series?
1 over E.
Okay. Would you agree that E is 2.7, so that's less than 1, so it converges? You agree? Now, what does it converge to? Well, since it's a geometric series, it converges to A over 1 minus R. 1 take away 1 over E. And A is the first number in the series. So if you plug n equals 1 into this, you get 8. And so it adds up to that guy, but I don't like fractions that have fractions in them, so I'll do that trick of multiplying by a special version of 1, in which case I now have a much nicer looking answer. So that guy converges, and this is what it converges to. And this guy here, you'll do a telescoping series on it, and I believe that it adds up to, it converges to 5. If that converges to 5 and this guy converges to that, then the whole thing converges. Suppose that diverged. Wouldn't the answer be the entire series diverged? Suppose that diverged. The answer would be the whole series diverges. But if both of them converge, then the complete series, the thing that's made up of the two joined together, also converges.
Does it
That's-
converge on 1 point or does it converge?
It converges to 5 plus 8e over e minus 1. That's what it would add up to.
Okay.
So
5 because of
question.
that. Yeah.
So, how is the A equal to 8E? Could you go over that real quick again?
Are you happy about A being 8 before I do the bit that comes after?
No, because I thought that if you plug in n equals 1, then that's what
Oh, you
the
should
A
get
would
that.
be.
Okay, there we go. 8 over E.
Okay.
Now you get 8. You're going to have to keep with me today. I'm sure I'm going to make a lot more. But the answer was.
Easy to get mixed up.
Now, the fact you know means you're understanding it is good. Okay, any more questions before we leave this guy and start the 11.3? Okay. 11.3 adds to our list of tests. And we've got quite a few. Let's see, what do we know? We know the divergence test, the geometric series test, telescoping series test, and I think that's it right now. So we're now going to add the integral test and the p-series test. I'm going to do the p-series test first because there's fewer of those questions. So let's tell you what a p-series is. a p-series looks like this. Looks like that. So an example of a p-series, 1 over n cubed, 1 over the square root of n, 1 over n to the 0.3, 1 over n to the 1.5, right? Anything that can be written as 1 over n to the power of something is a p-series. This is called a p-series p equals 1.5. This one is a p-series p equals 3. What would be the p-series for this one? One over the square root of n. What number is that the p-series for? Any takers? 1 over the square root of n.
What is the last one here? The n is
0.3.
something. like- Okay, thank you.
That one, right. So, any takers in that one? Okay, what fractional power is a square root? It's not meant to be a trick question. What fractional power is a square root?
1.5.
Right. So this guy is essentially that guy, right? So what p-series is 1 over the square root of n then? He's 1.5. He's a p-series 3. This guy at the end is a p-series 0.3. What's this guy? I'm not quite sure what the problem is. It's not a trick
1/2?
question. Yeah, that's all I was wanting. Right. Just a half.
I sorry, I was trying to, you got ahead of me, way ahead of me on that one, so I apologize.
Oh. No, not a problem. I'm not blaming you in specifics. I just was trying to get my head around why that one was causing so much issues, why we weren't seeing it. Do you see the pattern here, right? Whatever that power is the p-series, right? If that's a 3, it's a 3. If that's a half, it's a half. Now,
Is that
what
why
does
they
the
call it a
p?
p-series? Because it's a
Yeah.
power?
It's the p's for power. So the p-series for any p-series sigma n equals 1 to infinity, 1 over n to the p. Right, for any p-series, that's a guy that looks like that. If p is greater than 1, the series converges. And if the p, and the p is the power, is less than or equal to 1, then the series diverges. Which means you do not have an awful lot of work to decide, does somebody converge or not? So look at this one, 1 over n to the power of 1.5. You see that one there? 1 over n to the power of 1.5. It's a p-series and the p is 1.5. Isn't that bigger than 1? So this one converges. Okay, would 1 over n cubed, right, this p-series here, does that converge?
It's greater than 1.
Which means it converges then. What about the 1 over square root of n, which is a p-series of a half? What does that do? Converges or diverges? It has to do one or the other.
Diverges.
Yes, diverges. And the last one, the 1 over n to the 0.3, since it's a p series of power 0.3, and 0.3 is less than or equal to 1, this one also diverges. So essentially, for a p series, right, anybody who looks like this guy here, all you need to do is look at the power, the p. If that power is bigger than 1, you're looking at a series that converges. If that power p is less than or equal to 1, you are looking at something that diverges. Do you think it matters if you put a 10 on the top instead of a 1? Would that change the convergence or divergence? What do you think? If something converges when there's a 1 in the top, do you think it's going to change just because you put a 10 on the top? No. So you can actually do the p series with a little bit of flexibility. Won't that one still converge? Won't that one still diverge? And won't that one still diverge? Do you see the number that might be or might not be in the top has no effect on your final conclusion? Don't you? Only thing you look at in these particular very specialized series is what's the power on the ball, right? That's the only thing that really matters. Top can be 1,000,000 or 2, won't matter. Your answer will still be converge, still converge, still diverge, and still diverge. So let's take a look at the very few that kind of fall into this category. It's nice when it happens, but it doesn't happen really. I'm getting my things talking to me, which I don't like. Let's find 13. Here's 13, right? So this is a version of question 13. And we have 9n to the negative 1.3 plus 6n to the negative 1.6. Now, although this is a p series, you have to do a fair amount of work before you can actually use the test, right? Before you can use this test. For starters, this is not a fraction, right? So that's the first thing I'm going to do. I'm going to rewrite this guy like that and that. Are you comfortable about negative powers can be written as fractions with positive powers? This is a p series, right? This guy here is a p series. What's the p value? No trick questions here. What's the p value?
1.3.
1.3.
Yeah, simple as that. And because that is a big number, big means bigger than 1, doesn't that converge? Now what about this guy? Well, he's also a p series, but his p value, right, his power is 1.6. But that's bigger than 1, so this converges. What conclusion can you make if a series is made up of 2 pieces and each piece converges? Will the original thing, right, these 2 pieces, will the original series converge or diverge now? If it's made up of 2 pieces that converge.
Well, converge.
Converges. Can you imagine that that guy converged, but let's say this was a different guy and this diverged, right? If one piece converges and the other piece diverges, won't your conclusion then be the entire series diverges, right? If one bit's broke, they're both. Now, I think the last combination is even more obvious. If that piece diverges and this piece diverges, then definitely that one diverges, right? So diverging is kind of destroys your ability, right? If anything, any piece of the puzzle is a divergent piece, doesn't that mean the whole thing is going to diverge, regardless of what the other pieces may or may not look like? How are we on that one?
Well, one thing
Yeah.
I'm kind of, it's probably not a great question, but it
No,
seems
they're
like
good
before
questions.
on the other tests,
Mhm.
when we found out something converged, we found an actual value that it converged
Correct.
at.
Yes, you're right, we did. You
But
don't
what-
find them in these.
Okay,
If you wanted to know what they converge to, what you do is get a computer program and say, add the first couple of billion together and tell me what it gets close to. Most series, we don't actually know exactly what they add up to, right? There are a few exceptions to that, geometric series, for instance, and the telescoping series. But most of the time, all we end up doing is say it converges. And in some cases, we can estimate what it adds up to, but that would simply just be, add up a couple of hundred terms and see what we get. And there are other series that we haven't met yet, where if we know it converges, we can at least say it adds up to something and the answer's between 5 plus or minus 0.2. So we can put a little arrow band on it, like a little tolerance. But no, we're not going to calculate totals for these guys. If they converge, that's pretty much all we're being asked to find.
So how would this work if you were to put it into like GeoBra or something like that? Like, how would you differentiate from what's a sequence and then what's a series?
Oh, I think you'd have to look up the YouTube. I can make sequences happen on GeoBra pretty easily. And if you go back, you'll look at a video and it'll show you the setup. I don't know how to make a series happen. I'm not saying it doesn't do it, but I don't know how to make it do it if it does. If you want to visualize it. But can we pretend that n represented how many terms you were adding up? So you'd have the first term that would be here, and the second term, the total would be here, and then the third term would be here. If something converges, wouldn't what we call the partial sums level off at some number up here? And that would be an example of something that converged. If something diverged, wouldn't it just get bigger and bigger forever? So a converging series would be if you just add up the first 10, 20, 30, 40 terms, would there be a leveling off in the answer? And a diverging one would be it would just keep getting bigger with no leveling off.
Okay.
Okay. I mean, have a look it up. Who knows? There might be somebody who's figured out how to make GeoBra do series. I'm sure it's kind of possible. I just don't know how to do it. Now, because not because, but these series do tend to have other things put in them because P series are too easy. I mean, if I just gave you a question, does that converge or not? Wouldn't you say P equals 2, it converges, right? Too simple, right? So instead of giving you a straightforward question, what they'll give you is something that you have to work on. So here's a different version of something you have to work on. This is a version, this guy here, is a version of question 5. Now, superficially, that does not look like a P, right? But we can make it happen. I'm going to split it into two distinct pieces. Are you comfortable about how I split this fraction into a root n over n squared and a 2 over n squared? You comfortable with the algebra? This guy gets split into 2 pieces. Now, do you recognize this fella as a P series? P equals 2, and so it converges. That wasn't too painful. Now, this guy needs a little bit more work before it's truly a P series. Essentially, that's a square root of n on top and an n squared on the bottom. So if I wanted to simplify it, I might call it n to the half over n squared. And then, are you happy about where the 3/2 would come from. Right, take half away from this 2 and you get 3 halves left. So that guy is him. And now I can see a p-series. And this has a power of 3 halves. Right, and that's bigger than 1, so this also converges. And so the entire series, converges. So we are given a series that superficially doesn't look like a p-series. But if you break it into 2 pieces and then work on at least one of them so it looks the way it needs to look, this is a p-series, so is that. 2 guys converge, the whole thing converges. Any questions about that one? Okay. This is the last one in the p-series. There's not so many of those. Question 4. We're being asked, does that converge or not? Well, I need to have a formula for this guy. This is the first guy. This is the second guy. This is the third guy. This is the fourth guy. I need to figure out what the general nth guy would be like. Okay. So we're looking for a formula to make this guy happen. Well, let's take the easy part. Can I call that guy 1? 1, 1, 1, 1. Everybody in the top is 1. The second guy is 2. The third guy is 3√3. And the fourth guy is 4√4. What would the nth guy be? Look for patterns.
In root in.
I agreed. Which means we now have the formula for the series. It's n equals 1 to infinity, 1 over n root n. Of course, I need to do just a little bit of algebra on that to make it in a form that I can use a p-series on it. That's basically n to the 1. That's n to the half. If you multiply them together, you get n to the 3 halves. Are we okay with that algebra? N root n gets you n to the power of 3 halves. This is a p-series, right? That's what p-series look like. Its power is 3 halves. Let's finish with an easy question. Does that converge or diverge?
Converges.
And that's us finished. Anytime you get a p-series and the power, let's see if we can find it over here, and the power p is greater than 1, it converges. And if the power is less than 1, it will diverge. How are we doing? Any questions before we look at integral tests? Okay. Now, there are many more, as you can see, questions that deal with the integral test than there was for the previous one. So let's look at how that one works. I'm going to rewrite it slightly different from usual, but there's a reason for that. For any series, sigma n equals 1 to infinity, and I'm going to call it f of n. Now, normally we just call it, a of n, but f of n is okay. So for instance, see this guy here, this would be f of n, right? This guy here is f of n, this is f of n, right? So whatever goes here is basically all f of n is, right? So for any series, right, any series you can think of, written in this format, if n of f of n is positive, so it can only have positive numbers, no negatives allowed, and f of n is decreasing, and the integral from 1 to infinity of f of x dx convert then the series, meaning this guy, also converges. And if this is true, right, it's positive and it's decreasing. If the integral from 1 to infinity of f of x dx diverges. So converges just means that this integral is equal to 4, right, or 44. It's equal to a number. And if the integral diverges, essentially for most situations, that means the integral is infinite, then the original series also diverges. And that is called the integral test. The integral test requires an awful lot of work. You don't even do it unless these two conditions are met first. That guy must be positive, right? So, you know, the individual terms have all to be positive, right? You can have some plus and some minus. Second, it must be always decreasing. If those two things are true, then you can find the integral. And if that integral is a number like 42, the series converges. If that integral is infinitely large, then the series diverges. And it's pretty obvious, I think, why it's called the integral test, right? You integrate things. So let's start with the series. Looks like this. I would like to know, does that series converge or diverge? So here's my series. So the function f of n is this guy. Are we good? Now, we should go through these two tests every time before we do it. And I am going to do it for this one. But for time constraints, I'm not going to do it for any of the others. You'll just have to assume that I've done it and it works, right? Because I want to get into the good stuff. So let's look at this and prove it's positive. Now, when you're talking about a series, the assumption is that n has to be whole numbers, right? It has to be 1, 2, 3, 4, right? So n over n squared plus 1. Would you agree that n is positive? Because it's 1, 2, 3, 4, 5. Would you agree that n squared plus 1 is positive? Which means the whole thing is positive. That's me proved that this is positive. Not much of proof, but it's a proof. Now, that's one done. Two's typically going to be more difficult. I have to prove that this thing here is decreasing. Way back in one of your previous calc classes, you could use something to prove a function was decreasing. Do any of you remember how you could prove a function was decreasing?
Do you have to
Would
do
it
it?
be if the derivative is negative?
That's it. The derivative is negative. So what I'm going to do here is I'm going to differentiate this guy and try and prove to you that that derivative is negative as long as n is 1, 2, 3, 4, 5, right? Anything that's positive and big. So the original function looks like this. And the reason I'm only going to do these two steps once is just a time thing, right? It's not that you can't differentiate things. It takes forever in a day if you have to do it for every question. So this is f, and this is g, and we're going to differentiate it, and we're going to get what's called the quotient rule. So it's f dash g, take away f of g dashed, all over g squared. If you differentiate that guy, you get 1. You leave the other guy alone. Take away, you leave this guy alone, and you differentiate that guy. And the whole thing is going to be over n squared plus 1. 1n squared plus 1 take away 2n squareds. That gets me 1 take away n squared. All over n squared 1, n squared plus 1 squared. Now I'm going to prove to you that this is negative in a very kind of simple way. Would you agree that something squared is always positive? Would you agree that 1 minus n squared is going to be negative as long as n is reasonably big, right? 2, 3, 4, 5. Then isn't a negative thing divided by a positive thing negative? And so what the circles are just for emphasis, by the way. They don't need to be there. I'm just emphasizing them. That means the derivative is negative. So we're decreasing. And that's pretty much the only time I'm going to do those two steps. For the rest of these questions, I want you just pretend that I did it, but you really should do it to get practice at it. So the final stage is to find this integral. And if this integral converges, then my series converges. If this integral diverges, my series will diverge. So I want to find the integral from 1 to infinity of f of x dx. I want to find the integral from 1 to infinity of x over x squared plus 1 dx. Now, in Calc 2, you found a way to integrate, right, these types of integrals. Can anybody remember what you did to find an integral where one of the limits of integration was infinite, as it is here? Any suggestions?
What was the question? I'm sorry.
Right. How do you find this integral? You did it in Calc 2. How would you go about finding this kind of integral where one of the limits is infinite? Okay, here goes. You do the limit as t tends to infinity of the integral from 1 to t. Does that ring some bells? Do you remember doing that? Okay, now put it over here because I need lots of room. But I've changed my mind. I'm going to do it over here. Don't worry about the t right now. Just focus on integrating that. We have a number of techniques that we use to integrate things. We have the power rule, which this is not. We have standard integrals, like, oh, we know what the integral of e to the x is. Like this. Third, we have u-subs, substitution in other words. And 4, we have integration by parts. So that's your shortened list that you can pick from. Well, this thing's not bending the way I want it to. There we go. Okay. What technique shall I use to integrate this fella? It's one of
Three.
those three. Agreed. We're going to do U subs. Now, what is the correct U sub? Pretty straightforward, this one.
N squared plus 1.
Okay. Now we'll differentiate with respect to x. We'll do the crossover and divide both sides by 2x. This integral, and I don't put limits when you do a U sub, I leave these blank. I have an x over a u times a 1 over 2x du. If things work out well as they do here, this cancels. And I now have 1/2 1 over u, which is a good way to write this guy. So the original integral, which wasn't really doable, has now became this guy. Do you recognize that the integral of 1 over u is natural log of u? So what we get is 1/2 the natural log of u. Okay, now I'm ready to do this guy. It's going to be the limit as t tends to infinity. Right. Oh, I forgot one thing. It now becomes 1/2 the natural log of x squared plus 1. So it's going to be 1/2 the natural log of x squared plus 1, evaluated here and here. So at x equals 1 and at x equals t. So it's going to be the limit as t tends to infinity. If you plug in t, you get 1/2 the natural log of t squared plus 1. Take away 1/2 the natural log of 2. So we've finished integration and it ends up being this mess. Now we're going to find out what happens to this when t goes infinite. And I'm just going to do brute force. If you make t infinity and then you square it and add 1, would you agree you get infinity? And isn't the log of infinity infinity? And isn't half of infinity still infinity? So you get infinity. Does it really matter what this piece does when one of the pieces is infinite? No, right? Taking a little bit away from infinity is not going to make it any less infinite. So we have that as our answer to the integral. That means, in the jargon that we use, that means that the integral diverges. Right? If the integral's infinite, it diverges. So we can now say that the series also diverges. By the integral test. So essentially, you found out what the integral of this guy is. If the answer is infinite, it diverges. And if the answer is a number, it converges. How are we doing? Any questions? Okay. Choose some more practice, the better. Pick something that we... By the way, the question I just did was a version of question 1. So here's question 2. Whenever this thing goes, because it sounds to me like its charge is going rapidly, could somebody say, I can't hear you anymore, so I can go to plan B? So are you hearing me okay right now, my son? Yeah, because this lady's voice keeps on saying battery is low, and she's been saying it for a while now. So we're looking at n equals 1 to infinity of n squared e to the negative n cubed. And we are going to find out if this series converges or diverges. Well, can we assume that I proved that it was positive and it's decreasing, right? That would take about 5-10 minutes. Let's just say I did that, and it did. So now I'm going to find the integral from 1 to infinity of x squared e to the negative x cubed dx. From my list, this list here, what method will we use to find this guy's integral?
Integration by parts.
It looks like it, and very often it is, but in this case, it's not. If that had been e to the negative x, it would have been, Eric. And the fact I've done a u sub might make you think that I was not going to do something that wasn't a u sub. But this, in fact, is a u sub. Right? Now, if it was x squared e to the x squared e to the negative x, things like that, integration by parts would have been the way to go. If you tried integration by parts, I think in a matter of a few minutes, you'd realize it wasn't going to work. And then you'd restart the question and try something else. Now, since I've said it is going to be integration using u subs, what would be the u sub in this question? What would the u sub be in this question?
It's gonna be the x cubed.
Okay, let's do that version. So you differentiate, you get that guy. You do the crossover, and you isolate by dividing both sides by 3x squared. That's pretty standard. Right? So my integral now becomes x squared e to the negative u, and the dx is 1 over 3x squared du. These guys cancel out, and I now have 1/3 e to the negative u du. Much easier integral, right? Now be really careful. I'm about to do a deliberate mistake. Oh, if you integrate e to the negative u, you get e to the negative u, so the answer is 1/3 e to the negative u, which is 90% right, but what's missing? Because something is missing.
The negative
was-
sign is using, and also the don't you have to substitute back in x cubed for u
Yeah,
at some point?
right at the end, you're right. The negative's the important part right now. Right? If it was e to the 2u, wouldn't there be a times a half going on here? Right? If it was e to the 5u, there'd be a fifth. E to the negative u, there's a negative 1 going on here. And then you turn it back into, just like you said, that guy. So, ready to continue? It's going to be the limit as t tends to infinity of negative 1/3 e to the negative x cubed evaluated at x equals 1 to x equals t. Are we good? Now, it's going to be the limit as t tends to infinity of negative 1/3 e to the negative t cubed. Take away a negative is essentially add. 1/3, put in 1 here, you get e to the negative 1. So just cutting some corners, that's what we have to deal with here. And I'm going to rewrite this in a slightly different form to help with the limit. Okay. I'm now about to put t is infinity, right, in here. So it's going to be -1 over 3 times e to the infinity cubed, which is just infinity, plus 1 over 3e, right? And -1 comes downstairs. Okay. E to the infinity is infinite. 3 infinities is infinite. 1 over infinity gets you a big fat 0. The result is 0 plus this guy. So it converges. And now we can go here and say that this converges as well by the integral test. Now, what some people unfortunately think is that you get more mileage out of this method than you really do. I agree this thing, the integral, converges to this 1 over 3e. That doesn't mean that this guy converges to 1 over 3e. It just means it converges to some number. And that's it. It doesn't mean it's this number. It might be, but the chances are it's definitely not. But it's a number, and that's all we can say for sure. And if you're wondering, well, why isn't it that number? Can we pretend that the shape looks something like this, right? The integral. The reason the integral test works is that these rectangles are essentially the individual terms of the series. Now, do you see these rectangles? Aren't they slightly lower than the curve? And so if the area under the curve is a number, won't all these rectangles add up to something as well, right? They'll add to a number. Typically, won't the number have to be less than 1 over 3? So don't assume that you're going to be able to get more than you do. All you can say for sure is it converges, and then, you know, leave it alone. How are we doing? Let's find a diverger if I can.
I have a question.
Sure.
So when you say something converges at
Yes.
a number and the sum, is it the same thing?
What do you mean? Is it the same thing, Eric?
Oh, I mean, when you say that a series converges at like 5, then is the sum of the series also 5?
If I phrased it that way, yes. If I said a series converges to 5, its sum is 5.
Okay.
I do not or should not have said it here. The integral converges to 5. Pretend that's 5, right? The integral converges to 5. The series just converges. Nothing else.
Okay.
Now, geometric series, don't you say, oh, the series converges to 5, right? So in those questions, you can actually tell me what the series converges to, right? It has a number attached to it. Its sum is 5. But in the integral test, you can't really do that, not directly at least. Okay. So,
Isn't the integral kind of the same as the sum as far as
No.
area?
well, let's look. Do you see this guy here has a lot of little pieces that are much bigger than the rectangles?
Yep.
Well, won't that add up to a total of 1 over 3e, but won't all the rectangles add up to something that's less than 1 over 3e, but I don't know how less. I just know it's less.
Yeah.
That's
Okay.
that's kind of the reason.
Okay.
So let's find a diverger if I can. Never find one until you're looking for it. That converges. That diverges. Well, let's get this one out. She's talking to me again. This one happens to converge, but that's not my problem right now. Actually, I've done that one. That's a P-series. Forget that. I've done that. Let's keep going. Okay. Yeah, this will work. Why does this series start at 2 and not 1? And by the way, that's meant to be an N. Why does this series start at 2 and not 1? What would happen if N is equal to 1? What would this be equal to?
0.
And 1 over 0 is bad news. So now, does that change anything? Actually, not much, right? It just means it's going to be 2 to infinity, not 1 to infinity, right? That's pretty much the only thing that's going to change. So can we assume that I've already checked that it's positive and that it's decreasing? And we go right into the third phase, which is now we need to find out, oops, almost did it wrong there, the integral from 2 to infinity of this guy. Which means that we're going to find the limit as t tends to infinity of the integral from 2 to infinity 1 over x natural log of x dx. And if that integral ends up being 4, then the series converges. And if that integral ends up being infinite, the series diverges. So let's do it. This series is a U sub again. I think the next one I'll pick is an integration by parts, just to show you an integration by parts one. But this is a U sub. Who's the U sub? Which one is it? Not a lot of choices there. So who is it?
Yeah, ln of x.
Yeah. Now, if you were thinking just x, a U sub of x never does any good, because all that would happen is the integral would turn into 1 over u log u du, right? Nothing would change except the letters, right? So u equals x is never going to be a U sub of any use. But this one, what? Du by dx is 1 over x. If you do the crossover, x du equals dx, which actually is all I need, so I'll stop there. So it's going to be an integral 1 over x, no, oops, x u times x du. Oh, come on, that is too nice to be true, isn't it? Just 1 over u. And you integrate it, and you return it. Oh, would you look at that for an evil looking function? It's a natural log of the natural log of x. Well, you can live with that. You know, just trust the math and see where it leads. So it's going to be the limit as t tends to infinity of the natural log of the natural log of x evaluated at x equals 2 to x equals t, and I should have put t there. So it's going to be the limit as t tends to infinity of the natural log of the natural log of t, take away the natural log of the natural log of 2. That's a number of some sort. I'm not too concerned about that. This guy is going to be interesting. I'm going to do brute force again. So it's going to be the natural log of the natural log of infinity. Take away the other guy. All right, let's see if we can argue this one through. Would you agree that the natural log of infinity is still infinity? And the natural log of that infinity is still infinity. So don't you basically get infinity, take away a number so it's infinite? And that means it diverges. So that series diverges. And it diverges by the integral test. Are we good? Right. So really, most of today has been, can you integrate one to infinities, right? Because that's the major math that you're doing in every case. If that one is okay, then I'm going to move on to a question where you need to use integration by parts, okay? Just to show you that one. But is there any questions about this one that you want to do before we move on? Okay. We are looking at, and because they want to, they've changed it. Let's do that one. Okay, let's just assume that the function is positive and it's decreasing, which it will be. And now we're going to find the integral from 1 to infinity of x e to the negative 2x dx. Do you see the k doesn't matter? Couldn't it have been called n equals 1 to infinity or p equals 1 to infinity? It would have been the same series. Right. This is equal to the limit as t tends to infinity of the integral from 1 to t of x e to the negative 2x dx. Now, I've already promised that this is going to be an integration by parts, but let's see what makes it integration by parts. If that guy there had said e to the x squared or e to the negative x squared, wouldn't this be a user? Right? If that had been x squared, this would have been a user. It's an x or a 2x or a 5x. Ain't going to happen. Integration by parts. So let's do it. Now we're bringing out all sorts of stuff from Calc 2 here. Integration by parts. You call this guy F, you call this guy G. Integration by parts is essentially the closest thing it's nearest to is the product rule for integrating. It's how you integrate two things that are multiplied. And some of you have learned using the formula, the UDV method, and others use this formula, which is one I'm using. Do any of you recognize that formula, the integration by parts formula? Nothing that you've learned from Calc 1 onwards, in fact, nothing you've learned from 141 onwards disappears from math. Right? They reappear in all sorts of places. Today, for instance, is full of integration techniques. You know, next week we might be doing a lot of differentiation. Week after that, you know, who knows what we'll be doing, right? Everything that you've done in the past will come up again somewhere in math. So f of x is this guy. What does capital G of x mean that I have to do to this function here? What's capital G of x asking me to do?
Integrate it.
Agreed. So if you integrate e to the negative 2x, you get e to the negative 2x times a negative a half. You happy about where the negative? Take away. If you differentiate that guy, you get 1, and you put in that integral thing, you get this guy again. Make it look pretty. Okay, if you integrate this guy, you will get e to the negative 2x times another negative a half, which gives you negative a quarter. So that is the integral. So we are going to do the limit as t tends to infinity, the integral, which is this horrible mess, evaluated at x equals 1 to x equals t. You're going to get negative 1/2 t e to the negative 2t, take away 1/4 e to the negative 2t, subtract, plug in 1 here, you get negative a half e to the negative 2, plug in 1 here, you get minus 1/4 e to the negative 2. These two guys get you negative 3/4. That makes it a plus, so you're going to get plus 3/4 e to the negative 2. That's a number. I'm not really worried about numbers. This guy and this guy is a bit messy, so I'm going to pull out that guy, and that's going to leave me with negative 1/2 t, negative 1/4, this fella. And now I'm going to do a little bit more work, because that's not very easy to solve when t goes infinite. There, it looks like this guy, plus a number. Now, if I try to put brute force into this, all I get is negative infinity on the top and infinity on the bottom, in which case it's indeterminate form, and I do not get any meaningful answer, right? I cannot do the brute force, just plug in infinity, right? That's why I've had to rewrite it a little bit more work than you might think is necessary. What trick do you use to find a limit where the top and bottom are both infinite? This is from Calc 1. L'Hopital? Agreed. If you differentiate the top, you get this. And if you differentiate the bottom, you get. So we now have this fella. I can now plug in infinity in here. Would you agree that negative half over infinity is 0, so the answer ends up being a number, right? If you plug infinity in here, that just disappears, because negative a half over infinity is 0. And so you've got this, which means it converges. And so the original converges as well. So this series converges by the integral test. Any questions about that one?
Is there any point in which we're going through these processes, these tests, that we're gonna get to a certain step in the test that we could actually go back to the relative growth rate?
You
ratio?
might be able to do a relative growth rate. That's what t, and that's the power. So I guess I could have done it here without L'Hopital. So yeah, I can imagine some questions where the relative growth rate would allow you to tell here. You cannot do it up here, because all the relative growth rate will do is tell you that this becomes 0. But a lot of series, this can become 0, yet the series is infinite. 1 over n, for instance, is a good example of that. So if you were asking, can we do it away up here? No, there's no point. But could you do it down here? Yes. If you got an n cubed over e to the n, couldn't you just say relative growth rate, that's 0, and you'd be good to go.
Okay, yeah, I was just wondering if we can apply it later on, like as we're going
Yep.
through our steps.
Yeah, if you ever hit a point where you think the relative growth rate is relevant, right, that you could use it, and by all means do so. What I'm going to do for a few moments is just look at the homework questions and think ahead to how we would do the integral. Since I won't have enough time to do, all the ones that are there, and there are lots of, each one takes, 10 minutes. We'd never get through them all. Look at this guy here. Oh, by the way, when you're doing your homework, you say it's that one or that one, so you know you're going to get the answer right. So don't be lazy and just pick it if it says wrong. Well, come the online test, you're going to have real trouble, right? Because you have a 50-50 chance of doing it. Plus, in some of the later questions up here, where we go, do you see they ask you to put the answer in? So you need to integrate it anyway. So I've lost my place here. She's still talking to me. There we go. What method would you use to integrate that guy?
U sub
Agreed. What would the U sub be?
into the 10th.
Just into the 10 or anything else?
Oh, +2, yeah, and then 10th
Agreed.
+2.
And that comes out. By the way, that diverges, but you'll find that out at the end of the day when you do it. What about that weird one? What method would you use for question 12? And I'm going to go back and do that one after we finish this. What would you do in question 12? What method? I'll make it even bigger because the powers are so small you might not see them. There, no, there we go. Sneaky, that one. What would you do?
Is I don't know if this is e to the 1 over n to the 9th. Is that 1 over n to the 9th natural log e? Is that how you can express
Oh, I know what you're getting at. No, unfortunately, it's not, John. I wish it was. It would be a little bit helpful, but it's not. But I know what you're getting at. Okay, is it a U sub or an integration by parts? Which of those two do you think is more likely for this one?
It's not intuitive that's a U sub.
Correct. It's not intuitive, yet it is a U sub. Most U subs are much more obvious, right? This is not obvious, but it's still a U sub. So what the heck is a U sub? Which one? Not a lot of choices, right? I guess there's 3 choices. N to the 10, e to the power of 1 over n to the 9, or just 1 over n to the 9.
I think it's the last one, right?
Yes, it is. So I'm going to be doing that one. Do you see how weird that U sub is? U equals 1 over n to the 9. Not obvious at all, not intuitive. Most U subs do tend to be intuitive, but not that one. Oh, we've done that one. I'm just do a quick check because I may have missed something. Done that guy. Done a version of that guy. Oh, we've done those 2, yeah. Split that one up, done him. Oh. What method would you use for question 6? Well, that's maybe a bad question because it sounds like I'm asking you, is it a U sub or an integration by parts? Actually, it's neither of those 2. That guy's a standard integral. So let me show you what standard integral that is equal to.
So that looks like a P series Could you do a P series on that?
If that plus 29 wasn't there, I'd be right in there doing a P series. I agree. If it was just 1 over n squared, that would be a P series, wouldn't it?
Also,
Unfortunately,
if you're adding something to that power, then it.
yeah, that
P
screws it
series.
up. Right?
Oh, okay.
Now, if it had been 9 over n squared, that's still a P series. It's that guy that kind of wastes it, right?
Okay.
Now, if I said integrate x squared plus 1, I hope you would say, oh yeah, it's a standard integral. It's the inverse tan of 1. Great. There is a whole family of integrals like this one. So this, for instance, is x squared plus 9. And it is 1/3 the inverse tan of 1/3 x. And if you're wondering where does that 3 come from, it comes because of that guy. So for instance, 1 over x squared plus 25, right? That would get me 1/5 the inverse tan of 1/5 x. Do you see what's going on here? So if you wanted to find, in general then, 1 over x squared plus a squared, so we'd write it like this to make it more obvious who the a is. It's 1 over a, the inverse tan of 1 over ax. So if it was 100, you get a tenth and a tenth. If it was 36, right, you get a sixth and a sixth. So that's a standard integral. And that guy ends up being a tan, and you know, you do your thing and see what you get. So the one that I'm going to do next is actually the last one for today, if I can find it. It's that e, the 1 over guy that we were looking at a moment ago. Here we go. So we are going to find out whether or not this thing converges or not. Is that okay? Can you see that, or is it over the top? It's hard to tell sometimes with my screen. No, we're good, okay. Now, can we just assume that it's positive and decreasing, because I don't want to spend 10 minutes doing that bit, right? And now we're going to find the integral from 1 to infinity. And I hope that my thing on my ear lasts long enough for us to get here, because she's just spoken to me again. Right, we're going to get that. And that becomes the limit as t tends to infinity of the integral from 1 to t. Just repeat everything. Anybody got a gut feeling about this one? Do you think it's going to converge, or do you think it's going to diverge? It's very hard to tell, but you got a gut feeling? One way or the other? What do you think? Nobody going to commit? I mean, you're 50-50 chance of guessing, right? Because it typically is a bit of a guess, isn't it? You know, your gut feeling sometimes is right, sometimes it's wrong. Okay, this one's going to, I might change my mind now. No, this is going to converge. That's my gut feeling. Let's see if it does. It's a U sub. And the U sub is that guy. Well, if I want to differentiate that guy, I better call him that fella. Now I'll differentiate. Power roll. Do the crossover. Divide both sides. And we're finished with that bit. So the integral becomes e to the u over x to the 10 times 1 over negative 9 x to the negative 10 du. And if you're beginning to panic here a little because it looks like the x's aren't going to cancel, hold that thought for just a little while, right? Isn't x to the negative 10 on the bottom the same thing as x to the plus 10 on the top? You agree? Negative power on the bottom, positive power on the top, which means we get a cancel. So we now have negative 1/9 e to the u du, which integrates really nicely as that, which then becomes, when you turn the u back into the guy, it then becomes that guy. Are we good? Okay, so I'm going to be plugging in here. So it's going to be the limit as t tends to infinity of negative 1/9 e to the power of 1 over x to the 9, evaluated at x equals 1 to x equals t. So it's now going to be the limit as t tends to infinity of negative 1/9 e to the 1 over t to the 9. Take away, 2 takeaways make it an add, 1/9 e to the 1. Okay, I can do brute force on this. Negative 1/9 e to the power of 1 over infinity to the power of 9th plus the number 1/9. Okay. What number is 1 over infinity to the power of 9? Actually, 1 over infinity is the same number. What do you get? Big fat 0, I agree. So we get negative 1/9 e to the 0 add 1/9 e. And that's a number. It's 1. So you get negative 1/9 plus 1/9 e. It converges to a number. And so this guy also converges by the integral test. Are we good? Before we finish for today, let me show you some interesting brute force situations. The inverse tan of infinity is not infinity. The inverse tan of infinity is in fact pi over 2. Because what you're finding here is what angle has a tangent of infinity, and that answer is pi over 2. The sign of infinity is essentially undefined because it doesn't really have any obvious finish. Whenever something's undefined, it means that if it's part of your answer, it diverges. Okay, just it diverges. What would that guy give me? 0. 0. 0. Does it matter if there's a 10 or 100 or 1,000? No. Anytime you see infinity on a bottom, aren't you going to make the answer 0? 1 over infinity or any other number over infinity is 0. So when you're doing brute force questions, bear that in mind. Okay, any questions? We're going to kind of finish off here. It's a miracle this thing's still working, but I'm pleased. Any questions? Right, so we've kind of finished an actual stopping point, and when we see you next week, we'll be moving on to a new section, and try to remember what the new section is. Well, obviously it's 11.3, and I remember now. We're going to look at the comparison test and the limit comparison test, and that's next week's.
So on number 12, real quick,
Mhm.
because E had a fraction in its E to some fraction.
Yeah.
That's why we couldn't use the rate, right?
Correct. We don't know what that is. Yeah, if that was e to the 9, yeah. If it had been something like e to the n over n to the 10, let's just make it nice. Wouldn't that win? And the answer would be infinity. And if you're adding up a whole load of infinities, it diverges. And that would be the divergence test we'd be using, not the integral test.
Okay.